Hello everybody, my name is Mark Herndon and I'm going to talk to you a little bit about NTFS file compression and how it can affect file recovery and carving software. We're actually going to come back to this presentation here a little later, but first I wanted to give a little bit of a demonstration. I've done a lot of pre-setup here in advance, so I'm going to run you through what I've done. You can see here this is a Windows 7 virtual machine where I have two NTFS volumes created. They're about 100 megs each. If I show you this first one here, you'll see volume 1 compression is not enabled, and on volume 2 I have it enabled. This is just a built-in feature of NTFS, of course. It can be enabled in whatever version of Windows you're running. If I show you volume 1, I've got about 30 files, everything from pictures to office documents, text files, PDFs, just a wide assortment of different types of files that a carver could hopefully go in here and extract later on. And I have that same set of files here on volume 2. You'll see the slight difference is that the names are colored blue. This is Windows' way of showing that those files have been compressed on the disk itself. So after creating those two volumes, what I did is I unmounted them from the Windows machine here. Saved off the VDI or the VMDK disk image, and remounted it here in SIFT, which is a Linux forensics virtual machine. If I go ahead and do a fdisk and put in the password, then what you'll see here, we have a partition here, dev-sdb1. This is the first NTFS file system. This corresponds to volume 1. And then there's a dev-sdc1, which is also an NTFS that corresponds to the second volume, the compressed one. I took these two volumes here in SIFT, ran them through a DD, which if you're not familiar with, there's other tutorials on Sci4 explaining what DD does and how it can make a forensic image out of a file system like this. And then I took those images and ran them through another tool called Scalpel, which is of course a file carving software. And again, if you're not familiar with Scalpel, there's tutorials on Sci4 for that as well. So I have the output. Here's my Scalpel directory. I have the output from the two images, image 1 and image 2. So if we take a look at image 1 first, you'll see the normal assortment here. There's a bitmap that it was able to extract. There's some GIF images, some JPEG images, and of course some of those office files. I've gone in here and pre-named them so we'd know what they were, but this is a copy of the Cat in the Hat, for example. We'll let it load so you can see that it did extract the file. And so there's your readable file as you would expect. Now if I instead go look at image 2, which came off of our compressed volume, you'll see a different story. Well, there's no bitmap folder for one, but if we take a look at the GIFs, you'll see there's no thumbnails because these actually did not carve properly. They're all corrupted, which I'll demonstrate here by opening one. A similar story on the JPEGs. You'll see there was one JPEG able to be carved. That file coincidentally was stored entirely uncompressed on the compressed NTFS volume. That happens sometimes with compressed files. So that one was able to be extracted. You'll see this other one over here was maybe the first 3/4 of it was stored uncompressed, and then the last bit got corrupted because it was compressed on the platter. So basically what I wanted to show you here is exactly that. If you take an NTFS compressed data set and you run it through tools such as Scalpel or Foremost or really any other type of recovery software like this, this is what you should expect to see. You should expect corrupt outputs that just don't represent the original files that went in. Now the reason for this, of course, is that the actual data stored on the disk is not the same between the two, and I have this demonstration here to show that. This is actually image 1 opened up in a hex editor, and this is image 2, and what I've done is I've gone and found a bitmap image. You can tell from the file signature this is a bitmap, this is the size of it. This is actually the identical bitmap image on the two volumes. And on the left, you'll see what you'd expect in a bitmap. Lots of white space, FFF, just repeated over and over and over. On the right-hand side, you'll see that's been compressed down. In fact, this looks almost nothing at all like this uncompressed version. And if you were Scalpel, you were coming through the volume here from the top. You're looking for stuff, and then you see this file signature here. It says, "Oh, I found a bitmap." But then when you start saving all of this data off to disk to a file, it of course doesn't represent what you thought you were carving. And so that's really why I've put this presentation together, and this demonstration here is to talk about what we can do about that. So without going into all the technical details, this is a 30-slide presentation here that describes in detail how all this compression works. But without going into all that, basically what happens is the algorithm takes 16 clusters, what it calls a compression unit, and it attempts to compress that data. As you can see here on top, if it's able to shrink the data by at least one full sector, from 16 down to 15, it'll go ahead and store it that way on the disk. What you'll see in the middle is maybe an example of something like that JPEG we saw earlier, where if it attempted to compress the image, it would actually grow in size, or maybe it would only, save half of a sector, for example. It couldn't save a full sector worth of space. In that case, it won't attempt to store this larger set of data. It will store the original uncompressed data. So what you end up with is a mixture of compressed and uncompressed data sharing the same media volume. And in fact, this is just another example. It's not quite as easy as what was shown on the last slide. You actually do get a lot of interleaving of compressed and uncompressed data even within a single file, where different portions of the file compress better, and it'll swap in and out of compressed mode as the file's being written. So we're going to skip forward through a lot of the technical details again. This is an interesting view of a hex editor that I put together here with some color coding. What this is meant to show is kind of the breadcrumbs and the metadata that the compression algorithm leaves behind. The green data is actually left uncompressed, the purple data is compressed, and the blue and red data represent, like I said, that metadata that kind of helps you decode what's really going on here. So this is the type of structure you'd expect to see. In fact, this is one of those bitmaps. Again, you can tell from the file signature, this is what you would expect to see with a compressed file such as a bitmap. And so we're going to skip forward again. Basically, I've got kind of a demonstration here in the slide deck that discusses how you would step through and you'd follow the trail of breadcrumbs to slowly kind of build your output here. I'm not going to go through all that, but just to show you, this is kind of how that works, where some of these little tags indicate that the data is uncompressed. Others, these red ones, are indicating the data is compressed, and then the little purple tags are telling you where to go back and find the original data that it's pointing to. So the example here maybe of the word "the" is actually this second bunch of data that we're looking at here, which is saying go back 136 bytes in the stream that you've been working on and go grab 5 bytes, which ends up pointing at this space, the word "the" and another space, which gets dropped into the stream, and you move along. So that's kind of how this works. It's like following a trail of crumbs through your data set. And so I've got some other, again, technical details, some corner cases and things here in the slides if anyone is really interested in digging into this in more detail. But I just wanted to focus more so on some final thoughts here and then giving another demonstration. What we're really trying to get at is that NTFS compression, it's a built-in feature of the file system. It's really easy to enable. It can be enabled on volumes as small as 7 meg to as large as 16 terabytes. And as we showed with Scalpel earlier, just by simply clicking that checkbox, it makes it very difficult for typical recovery and carving tools to extract data from such a volume. Now, I'm not claiming this is, perfect protection. I mean, this is not encryption. There's nothing secret about this. But that's really the point. Because there's nothing secret about it, we ought to be able to fix this problem. We ought to be able to see through this compression if maybe we're performing an investigation and the image we've been given came from somebody's compressed laptop, for example. We should kind of feel foolish if we can't see through that and get to their data. And so that's what I am attempting to achieve here with the next demonstration. And so what I want to show you now, this is a third image that I made. It's called Comp Alice. Basically, I took the file Alice in Wonderland from Project Gutenberg and I put it on a 100 meg drive. It's the only file on that drive, but the drive is compressed. which you can kind of see pretty obviously here. Up towards the top, this is very human readable. You'll see Project Gutenberg's Alice's Adventures in Wonderland, Lewis Carroll, etc., etc. You start coming down a little further. I've highlighted an area here, author. You might expect to see Lewis Carroll, and clearly that's not at all what you're seeing. As you go further and further down into the drive, or I'm sorry, into the file, you'll see less and less human readable text. Basically, there's an occasional letter or two that can be made out, but it's definitely been compressed beyond recognition. And so again, if we were Scalpel and we were coming through to try to carve this file, this is exactly the set of bytes that we would get, and it would be of no use to an investigator. I mean, if this were an incriminating email, you might get some of the header information or whatnot, but then all the deals that are going on would be unreadable. And so as the final demonstration, what we have here is actually a file carver that I've been working on. You can kind of see the help and usage information displayed. The intent of this, as you can see, is to carve files from compressed NTFS volume images, like the one we have here with Alice in Wonderland. Of course, it'll act as a normal file carver as well. It'll carve uncompressed data, and it'll attack other file systems besides NTFS. But really, my intent when I built this was to make it go after compressed NTFS data, and then maybe in the future, if there's other file systems that have compression features as well, maybe this could be adapted to suit those. But what I wanted to show here, this is an output directory I'm going to use. There's currently nothing in it, and I'm just going to launch the tool here. I'm going to use the option, actually we're going to put in the name of the image here first, which was comp Alice. And I'm going to use the option for the output directory to put it over there in Alice demo, so that once it runs we can see what happens. And so you'll see it found a text file, a second text file, and now it's finished. You'll see what came up over here is an output directory for the two text files, as well as an audit log and a database. Here in the audit log, what you'll see is that it did say that it found two files, both of which were compressed, so that's a good sign. It was able to detect that those files were compressed, and it attempted to decompress them. It gives you the length and MD5 sums, of course, of what it found. And now if we go into the directory itself and we open up the file, you'll see here this is actually Project Gutenberg's Alice in Wonderland. And as we scroll through it, you'll see this has entirely been decompressed back to its original state, all the way down to the bottom. None of the mangled garbage that we had over here, obviously in the actual disk itself. And so that's the demonstration. Hopefully you guys enjoyed it, and hopefully if you're interested in this topic, as I said, you'll go back and look at the presentation I put together. It walks through all the technical aspects of what's actually going on behind the scenes here, and I just didn't want to get into that as part of this demonstration. I thought it would be more useful to show the good result, I guess, here of what can come from understanding how the algorithm is used. So again, thanks for listening, and I hope you enjoyed it.